Because eigenvalues and eigenfunctions of self-adjoint operators play such an important role in quantum mechanics, it's worth looking into their properties in a little bit more detail. So the first thing that I want you to notice is that the eigenvalues of self-adjoint operators are real. So how can we prove this? So let's take a self-adjoint operator and consider the eigenvalue equation. Now we can take the inner product of this equation with psi n but of course a is just a number, so in the inner product it's not a function of x, so the integral over x is not going to affect it, so we can just factor it out of the inner product. So we can factor on the right hand side an outside the inner product. On the left hand side, because a hat, the operator, is a self-adjoint operator, I can move it from here to here. So I can write it as this times an of psi of n. But the left-hand side is nothing but psi of n, a hat of n star, where the right-hand side is just psi n. So with a acting on psi n is just nothing but an psi n star, whereas on the right hand side it's, but then we can factor out an from the left hand side, and because there's a star here, an will come out starred, where we have psi n star is equal to an psi n. But we know that this is a real number, and therefore an star, this is becomes psi n. And on the other side we have an psi n. So these two guys cancel, and then we have an star is equal to an. So as claimed, we see that the eigenvalue of a self-adjoint operator is a real number. So another important property is that the eigenfunctions belonging to different eigenvalues of a self-adjoint operators are orthogonal to each other. What does that mean? So suppose that we have two different eigenfunctions, psi m and psi n are eigenfunctions of the operator A belonging to different eigenvalues am and an respectively. So then their orthogonal means that if I take the inner product between psi m and psi n, then that's going to be 0. So how do we show this? First, we assume that am has only one eigenfunction. So now let's prove this. So what we show is we apply A on, say, psi m, and then when we apply that, we get on the right hand side am psi m. Now we take the inner product of psi m with psi n. So here I have psi n, psi m. Now, because A is a self-adjoint operator, I can bring A and get it to act on psi n. So on the right-hand side, I have am psi n psi m. Now, what is this left-hand side? The left-hand side, it's going to give me an psi n psi m. And the right-hand side, I have am psi n psi m. So now we can write this equation as an minus am times psi n psi m is equal to 0. So now there are two possibilities. One possibility is that this factor is 0, and the other possibility is that this factor is 0. But we have assumed that an and am are different eigenvalues, and therefore this is not equals to 0. So that means that this has to be 0, and therefore we get psi n psi m is equal to 0. So what we have shown is that eigenfunctions belonging to different eigenvalues are orthogonal. So if we had normalized our eigenfunctions, then this would be true. Then we can combine these two equations into one equation, and we can write that as the inner product of psi m and psi n is given by the Kronecker delta. And this is known as the orthonormality condition.